So I'm going to talk about some problems in random testing. And this is in the context of building and deploying large-scale distributed systems. And I have just put AWS here, but many large companies are building very large geographically distributed systems which carry a lot of our critical infrastructure on the internet. Now, when you build these systems, you would like to make sure that they are working as you expect them to. And you can think of these distributed systems as computation nodes that are communicating over some network. Okay? And in a nice world, you would imagine that one node sends a message which is immediately received by everybody else, and then they all send messages back. And perhaps you can argue simply about these algorithms. But the real world is very messy. Because when you send a message to another machine, maybe the network has a latency, the message gets dropped, some nodes may crash, some nodes may have malicious behavior, and so on. So getting distributed systems correct is actually a very difficult problem. And in fact, there's a very famous quote by Leslie Lamport that said, a distributed system is one where the failure of a computer that you didn't even know existed can render your own computer unusable. So now the question is, how can we ensure correct distributed systems? And in the part of my research that Martin talked about in formal verification, the standard answer is something like this. You model your system in a mathematically precise formalism. You prove the correctness of the protocols. And perhaps you can generate the system in a correct by construction way by making sure your compilers and so on are all correct. And there is a large body of literature in research, and this is really one of these open questions in formal verification. How can you scale formal verification to these large-scale distributed systems? And it's not an easy problem. It's open. It will remain open for a very long time. Now, what practitioners do very often is that they just build the system and test it on random inputs. And this seems to be a bad idea, right? Because we said that, look, it's really complicated, very carefully design inputs and careful things must happen in the network for things to work correctly and so on. But it turns out that in practice, random testing is often surprisingly effective in finding bugs in large distributed systems. In fact, there's a very nice tool called Jepsen that you can download and run on distributed systems. It's a framework for just black box testing that does the following. It sets up a distributed system implementation. And then what it does is that as the system is running, it gives just random inputs to the system. And at some point, it says, OK, now I partition some nodes of the network from other nodes of the network. This just means that some nodes cannot communicate to some other nodes. And then at some point, it says, OK, now the nodes can communicate again. And just by doing this kind of very random exploration, it finds astoundingly many bugs in many different, very robust distributed system implementations. Now, there's a famous theorem in the distributed systems world called the CAP theorem, right? Which says if you have a distributed system, then it cannot have consistency, availability, and partition tolerance at the same time. And this is what Jepsen exploits. It says, well, I'll introduce a partition in the network, and either consistency or availability should break. And then I see what breaks, and then I go and ask the programmer if that was the intended behavior. And this is the source of many of the bugs that Jepsen finds. At this point, I would like to thank Virginia for making this point for me. So the rest of the talk will have little to do with large-scale distributed systems. But what we'll try to understand from a theoretical perspective is why this kind of random exploration is effective. Okay? Now, there is a little bit of math, sorry, as Virginia said. On the other hand, as you will see, the math is very sort of high school level. So I know that there are a lot of high school students in the audience. You will see that the kind of math we'll use to argue about these systems is something that you should be able to do quite quickly. And in fact, we shall do a proof in the course of the talk. Okay. So many engineers will tell you that given the right notion of depth, given the right notion of where to look for bugs, all bugs are shallow. So this is an intuition that goes into doing these random tests, because they say that, well, if I randomize the inputs in a certain way, I'm really looking for the underlying structure. And that's why I find bugs. So what we'll try to do is we'll try to relate this notion of depth with certain combinatorial structures that we are trying to preserve when we are testing these systems. And I'll focus the talk mostly on this kind of partition tolerance in a distributed system, right? So you run the system, then you partition the network, and then you bring the network back. And the notion of shallowness I will capture in some kind of algorithmic bounds on families of structures, and I will try to argue why that shows that random testing should be effective. Now, let me first define for you what this notion of testing is. So usually what happens is that you come up with a set of coverage goals for your system. And empirically, these coverage goals are related to your finding, your ability to find bugs, right? So maybe you say that, well, if I have enough tests that hit every line of code, then I think that I should be able to expose a lot of bugs. Okay? So this is purely empirical. This is not something that is a theorem. But of course, whenever you're testing a system, you have some idea of what kind of coverage you're looking for. And then you pick a set of tests. In our case, the tests would be, well, you can randomly isolate some nodes from some other nodes, but you have a space of tests. And then what you do is you pick a test, and you see what coverage goals it covers. Then you pick another test, you get some more coverage, and your goal is to come up with a lot of tests so that you cover all the coverage goals that you want to have. Okay, so this is the notion of testing. And we'll call a covering family of tests, that is a set of tests that cover all your goals. And if you have a small family that is a covering family, this means that you have efficient testing. By testing the system on a small number of inputs, you are able to cover all your goals, and this will be empirically related to your ability to find bugs. And in random testing, you do this, but you randomly pick these tests, right? So at each step, you pick independently and randomly a test from your space of tests using some distribution. And a natural question then is, will random testing find a small covering family, or under what circumstances will random testing find a small covering family? And it turns out that there is a relation between the probability of hitting a goal and this notion of a small covering family. So imagine that you fix a particular coverage goal. You can ask the question, what is the probability that a randomly chosen test will cover this goal? And imagine that there is some way, that there is some calculation that you can do that gives a lower bound on the probability that a particular test covers a fixed goal. Then you can ask, well, can we characterize the size of a covering family based on the number of goals that you have and the probability that a random test covers a particular goal? And it seems that this is a very general version of a problem, but there's a very cute mathematical argument that says that there is, with these parameters, there is always a covering family that is proportional to 1 by p and log of the number of coverage goals. And in fact, the result shows that, well, if you just randomly select a number of tests, then random testing is overwhelmingly likely to find such a covering family. Now, the proof of this theorem uses something called the probabilistic method. So this is a method in combinatorics to show the existence that a certain object with certain properties exists without constructing it. And it essentially says that, well, if I set up a distribution appropriately, and if I can show that the probability when you sample an object from this distribution that this object has the required properties greater than 0, then there must exist some element with this property, right? So if the probability of something is greater than 0, then that something must exist. Okay? And in this testing scenario, you can show this very easily, right? So we said that, well, I have fixed a goal G. the probability that a random test covers this goal G was at least P. That was our hypothesis. So the probability that a random test does not cover this goal is at most 1 minus P. Okay, so if you take k independent tests, what is the probability that none of them cover this goal? Well, it's at most 1 minus P to the k. Okay, just probabilities, right? Independent choices. Which essentially means that if I pick k independent tests, that is not a covering family, this probability is bounded by the number of coverage goals times 1 minus P to the k, right? This is just the union bound, right? Because k independent tests is not a covering family if there exists one of these goals that is not met, right? And the probability of that is G times 1 minus P to the k. But then if you pick k to be 1 by P times log of the number of coverage goals, then this probability becomes strictly less than 1. And the probabilistic method says, well, then there must exist some k tests that is a covering family. Okay? So it's a very cute, small argument that shows you the existence of a covering family, but of course it doesn't tell you how to construct it. But the same kind of argument can be used to say that, well, if you just sample these tests, then you are actually going to find a covering family with very high probability. So our next goal is to essentially come back to the picture that I showed you before. And for a particular instance where you want to show a nice result on random testing, what you try to do is you define what are the coverage goals, you define what is your space of tests and the probability space, and then you try to see if you can bound the probability that a randomly chosen test covers a fixed goal. If you can do these three things, then you can apply this result and get the size of a covering family. Now, we could go into details of these distributed systems, but let me just motivate the problem with a puzzle. And the puzzle has to do with ninjas. And ninjas are cooler than distributed systems. Okay? So imagine that you have a bunch of ninjas, and they're training, and they're given different kinds of weapons. There are two kinds of weapons. You can have a nunchuck or a star. And then the ninjas are put into two different teams. No? So the ones with one kind of weapon fight the ones with the other kind of weapons. And you say that, well, the training of these ninjas is complete if for every pair of ninjas, there is a round where they were in opposing teams, where they were given different weapons. And so you see, so in each round you put the ninjas in two different teams, and then you say that training is complete if for every pair of ninjas, there was some round in which they were in opposite teams. Okay? So how many rounds do you need to make the training complete? Well, a naive approach is you need order n square rounds. No? For each pair of ninjas, you have a round in which they are in different teams. But it turns out you can actually get a complete training in log n rounds. And here's one way to see this. So you have the ninjas 1 to n. Think of each ninja as a log n bit string that tells you the name of the ninja, right? Or the ID of the ninja. And in the ith round, you choose the round so that all the ninjas that have the ith bit equal to 0 are in one team, and all the ninjas that have ith bit equal to 1 are in the other team. So then why is, so then you have log n rounds, and why is this complete? Well, take any pair of ninjas. There must be one of the bits, one of the indices where their bits differ, right? Because each ninja has a different ID. And so in that ith round, if they differ in their ith bit, then in the ith round they were in different teams. Okay? So while the trivial solution seemed to take a lot of rounds, you can get a much more efficient number of rounds. And now you can actually generalize this problem and say, well, now there are n ninjas, but there are k different kinds of weapons, and you can ask the same question, right? So you now distribute the ninjas in each round into k different teams, and you can ask how many rounds do you need. And just as an example, well, here's an example with 3 kinds of weapons, and I will show you very quickly a complete training round where these ninjas are given these different weapons in different rounds. Okay, So coming back to this question, again, the naive solution says n to the k, right? So for every k tuple of ninjas, you pick a round where they are in different teams. But you can do better. You can actually do it in something that is exponentially in n, but really requires log n, grows with log n rounds. So this is actually exponentially better than the naive solution when k is constant. Okay, so what do these ninjas fighting have to do with distributed systems? Well, you should think of the ninjas as the nodes in your distributed system. So these are the different processes that are communicating. The weapons you can think of as, when you have a network partition, you identify each partition with a different kind of weapon, right? So if you have partitioned the network, the ninjas are in different teams. Now, each round of training corresponds to a test that you run in Jepsen. And when a complete training corresponds to a coverage notion that's called a splitting family of partitions. Okay? So a splitting family is essentially you want to find a set of partitions such that for every k tuple of elements, there is one partition where each of the k elements are in different sets in that partition. Okay? Going back to the ninjas, there is one round of training where each ninja is in a different team. And the reason why splitting families are interesting is because many of the Jepsen bugs that are found can be explained by a k-splitting family for a small value of k. Because, in a distributed system, when you partition the nodes, most of the bugs happen because, well, suddenly the leader is in a partition that does not have quorum anymore, and then there is something that goes wrong. Okay? So there are some specific examples, but they're not so important. Okay, so then what we have to do next is to apply our general result about the size of these covering families. We have to answer the following question. So what is the probability that if you pick a random partition that it separates a particular k tuple of nodes? And this is, again, a very combinatorial problem. And what I'll try to do is I will try to walk you through the combinatorial argument that shows that a small family must exist. Okay? So fix a k-element set from the set of n nodes, right? So you have n ninjas. Pick a particular choice of k ninjas. And you ask, what is the probability that if you randomly partition all the nodes, that this random partition splits S? And something gets split if each element in the set belongs to a different partition. Now, first you notice that a splitting partition uniquely corresponds to a map from the rest of the elements to S. In other words, if all the elements of S are split into different nodes, you can imagine that the ninjas kind of stand in different parts of the room, and every other ninja kind of goes and joins one of them. Right? So every function that you can define on these ninjas, you can think of as these k different people who are in different groups, and everybody else decides who they want to be buddies with. So of course there are n minus k elements that are being mapped to k elements. So there are k to the power of n minus k such maps. Okay? So our goal is to show that, to give a lower bound on the probability that a random partition will split this particular set. Okay. So the probability that this happens is then given by the number of maps that you can have from u minus s to s divided by the number of partitions of n elements into k parts. And combinatorists have a name for this quantity. It's called the Stirling number of the second kind. So essentially the probability that you're looking for is this number. Okay? Now, remember that the result that we want to get, so we get very optimal results if we can ensure that the probability that we are trying to get, the lower bound on the probability, is independent of the size n, right? So think of n as something that is very big. Think of k as something that is small. okay? Because the number of nodes in your distributed system can be very big, but many of these Jepsen bugs are explainable by network partitions of a small number of partitions. So can we get rid of n from this expression? And yes, we can do this by observing the following combinatorial fact, right? And again, if you, I think for most of you in high school, you should be able to work these out by yourself. It's just, I'm going to do it very quickly, and then you can check that I didn't make a mistake later. So the reason why this inequality holds is the following. So on the left-hand side, you have essentially the set of all or how many functions there are from n elements to k elements. Okay? And on the right-hand side, you have how many surjective functions do you have from n elements to k elements. Okay? And the number of surjective functions is essentially, you think of the k people in the range, and then you essentially make a partition of the n elements into these k pieces. Each piece in the partition is the pre-image of one of the people in the range. And then you can rename the range so there is an additional k factorial here. Okay? And so now if you use this inequality, you can essentially get rid of n from this quantity. You get something that depends exponentially on k, but it's independent of n. Okay? And then we can just plug in the old theorem that I showed you, that, well, I now have a lower bound on the fact that a random partition splits a particular set S, and that's only a function of k. Applying our general result, we know that there is a k-splitting family that is exponential in k, but just logarithmic in n. And again, this is one of the reasons, this is a good case. This kind of explains why you are finding a lot of bugs very quickly, because you see, n is a number that grows very big, but you don't need a large dependence. It just depends logarithmically on n. And k is small in practice. Okay, there are some, few more wrinkles that you have to go through, but let me omit that. But in case you're interested, there is a very nice inequality that you can try to prove. This is not immediately obvious, but you can try it as a homework exercise if you wish to show why this is true. All right. So that's all I want to talk about, random partitions and Jepsen and so on. But the general point I'm making here is that you can take an observed phenomenon that random testing seems to find bugs very efficiently, and you can kind of abstractly study the problem, just the theoretical reason why you expect that random testing works well. Okay? So in some sense, this is the role of foundations or theoretical computer science. We kind of take a phenomenon that we observe in practice, and we try to understand why this phenomenon happens using these kinds of mathematical tools. Now, here's one thing that we don't know how to do. So it turns out in practice, people don't do this kind of independent random sampling. What they do is something called fuzzing or guided random sampling. Instead of picking tests independently, what fuzzing does is the following. It picks some test at random, and then it does a local search around this test guided by some kind of coverage. So what happens, going back to our picture, is that you pick a test, you see what it covers, you perturb the test a little bit, so find something close by, you see what that covers, and if it covers something new, you keep doing the local search, but if at some point you see that you don't see any new behavior, then you stop the local search, and then you pick one more thing at random. Now, it turns out that fuzzing works really well in practice. It works much better than just pure independent random sampling, but we don't really know why it works so well. So I think one of the open questions that we have in random testing is when can we provide a theoretical explanation? And there are some barriers that you cannot prove a very general result that random testing will always work really well. On the other hand, it's a very natural question. Why does it work well in practice? And the other dual question is, by using this lens of randomized algorithms, can you design perhaps an even better fuzzing algorithm? And in fact, let me give you an example just from the last talk that makes me optimistic that you can find some results. Sometimes we can actually show that local search is provably better than naive search. And one of these examples is for KSAT. So for KSAT, there is a very nice randomized local search algorithm due to Schoening that shows that you can solve KSAT, or well, 3SAT in about 1.34 to the n time. Maybe it's less than 2 to the n. So in some sense, there is some hope that you should be able to prove a better than naive bound on this kind of random local search algorithms. So this is what I will say. Thank you for listening. Essentially, what I want to say is that random testing seems like a very empirical discipline, but I think there are some very nice theoretical problems there, and many of them are actually open. Thank you very much.